The digital multiplexer is a combinational logic circuit containing 1 to 4 control inputs and 2 to 16 data inputs for each data output. Some multiplexers even provide complemented data outputs. Basically, the digital multiplexer performs the function of a single-pole multi-position switch in which one of the data inputs will be connected to the output at any one time. The particular data input being selected is controlled by the control inputs line. Digital multiplexers are used when a selection must be made from several data sources and the information must be routed to one destination. This method of selection is often referred to as data routing. Here we see the equivalent circuit of a 4-input multiplexer containing 2 control inputs with 1 true output and 1 complemented output. To better understand the digital multiplexer circuit, we will examine this simple equivalent circuit. The 4 different data sources are applied at inputs I0, I1, I2, and I3. The control inputs are applied at S0 and S1. The outputs are taken from the complement output and the true output. In our example, we will assume the data is being applied at all 4 inputs. When control inputs S0 and S1 are low, we see that a high signal is being applied to all 3 inputs of AND gate A, which causes AND gate A to turn on with the data. AND gates B, C, and D will remain off. When AND gate A turns on, it causes OR gate E to also turn on. The OR gate then feeds the information into both outputs, true and complement. When control input S0 is made high and control input S1 remains low, we see that AND gate B turns on while AND gates A, C, and D remain off. When AND gate B turns on, it causes OR gate E to also turn on and transfer this data information from input 1 to the true and complement outputs. When control input S1 is made high and control input S0 is made low, we now see that AND gate C turns on, while AND gates A, B, and D remain off. AND gate C causes OR gate E to turn on and transfer the information to the outputs. When both control inputs S0 and S1 are made high, it causes AND gate D to turn on while AND gates A, B, and C turn off. Once again, OR gate E is turned on, and the data information from input 3 is transferred to the complement and true outputs. As you can see, by controlling the high-low sequences on control inputs S0 and S1, this circuit can be made to read any one of the 4 data lines at any time. Oftentimes, the multiplexer circuit is abbreviated as MPX or MUX. Here we see the SN74150, which is a 16-line to 1-line digital multiplexer IC. This integrated circuit contains 16 6-input AND gates, 1 16-input NOR gate, and 9 inverter gates. The SN74150 is capable of multiplexing 16 data lines into one output. A 4-bit code placed at the data select lines, which are used as the control lines, will determine which of the 16 input lines are to be routed to the output. The strobe input is used as an override to force the output into its logical 1 state. Since the output of this device comes from a NOR gate, the data is inverted from the input to its output. This IC has a typical propagation delay of 10 nanoseconds with a typical power dissipation of 225 milliwatts. Here you see the SN74151, which is an 8-line to 1-line digital multiplexer integrated circuit. Internally, this IC contains 8 4-input AND gates, 1 8-input NOR gate, and 8 inverter gates. You may not have noticed, but this IC has 2 outputs. One output, which is labeled W, provides the true information, and the other output, which is labeled Y, provides a complemented output. 3 data select lines labeled A, B, and C are used to determine which of the 8 input lines is to be routed to the output. This IC has a typical propagation delay of 15 nanoseconds with a power dissipation of 135 milliwatts. Here we see the DM8123, which is a quad 2-input multiplexer IC. This IC consists of 4 2-input multiplexers with a common input select logic and a common output disable circuitry. This IC allows 2 groups of 4 bits each to be multiplexed to 4 parallel outputs. Here we see the logic diagram of the DM8123. Even though this IC contains 4 outputs, its operation is the same as the previous multiplexer circuits just discussed. We will quickly examine this circuit to see how it works. The first thing you may notice about this circuit is the arrow pointing toward the body of each of the OR gates. These are special OR gate circuits which can produce a tri-state output. The output may be high, low, or placed in a high impedance state. When placed in that high impedance state, the devices are effectively removed from the circuit. The arrows may or may not be present on a diagram, but the line will always enter at the side of the symbol. One of the 4-bit inputs will be placed on inputs I0A, I0B, I0C, and I0D. The other 4-bit input will be placed on inputs I1A, I1B, I1C, and I1D. Also notice there is only one select line on this device. Therefore, the DM8123 can only select between 2 sources of inputs. When the enable input is at the logic 0 level, the outputs are conventional TTL. However, when a logical 1 is applied, the outputs assume a high impedance state. Both upper and lower output transistors are turned off. The resulting condition allows many devices to be connected to a common bus line without loading down or being loaded down by other devices on the line. Now let's examine the operation of this circuit. We will begin by assuming that all the data inputs are high or active and the enable input is low. When the data select line is low, inputs I0A, I0B, I0C, and I0D are made active. These AND gates then cause the OR gates to turn on and transfer the data from inputs I0A, I0B, I0C, and I0D to outputs ZA through ZD. And when the data select line is made high, inputs I1A, I1B, I1C, and I1D are made active, resulting in the OR gates turning on and transferring the information to the outputs. As you can see, by controlling the data select line, this IC can transfer bits of information at a time from 2 different sources. Now that you have a basic understanding of how the multiplexer circuit works, we will examine the demultiplexer circuit. Multiplexing was defined as a process in which many data sources may be connected one at a time to one output. Demultiplexing, on the other hand, is the reverse process, or routing data from a single source to various destinations. As you can see from this simple diagram, one input source can be directed to any one of several outputs. The output selected is determined by the control line. To better understand how this happens, let's examine a demultiplexer equivalent circuit. Here we see a logic diagram of a digital demultiplexer circuit. Notice that it looks very similar to the multiplexer circuit we have already discussed. The primary difference is the demultiplexer circuit has only one data input with several data outputs. To better understand the demultiplexer circuit, we will examine how this equivalent circuit works. We will begin by assuming that the data input line is active and that the data select control lines S0 and S1 are low. As you can see, and the gate A is turned on. Therefore, the data from this data input line is routed to output Z0. By making data select line S1 high and leaving data select line S0 low, and the gate B is turned on, allowing the information to flow from the input to the Z1 output. When data select line S1 is made low and data select line S0 is made high, and the gate C is turned on, which allows the data from the data in input to be transferred to the Z2 output. And by making both of the data select control lines high, and the gate D is turned on, allowing the information to flow from the data in input to the Z3 output. As you can see, By controlling the data select lines, the information placed at the data in input can be directed to any one of several outputs, one at a time. Here we see the SN74155, which is a dual 2-to-4 demultiplexer integrated circuit. Internally, this IC contains 8 3-input NAND gates, 2 2-input NAND gates, and 5 inverter gates. The SN74155 is a monolithic TTL integrated circuit featuring dual 1-line to 4-line demultiplexers with individual strobes and common data inputs in a single 16-pin package. The individual strobes can permit or inhibit each of the 4-bit sections as desired. When both strobes are enabled, the common data inputs sequentially select and route the input information to the appropriate output of each section. The data information applied to input 1C is inverted at the appropriate output, while the data applied at 2C is not inverted at the output. The SN74155 has a typical propagation delay of 17 nanoseconds with a power dissipation of 125 milliwatts. Here we see the DM8223 IC, which is a 1-line to 8-line demultiplexer. This IC is TTL compatible. The 8 outputs, 0 through 7, are capable of driving 10 standard TTL loads each. The 3 address lines determine which output receives the data information. The typical propagation delay of this IC is 35 nanoseconds. We will now pause for a short review of the material just discussed. You have seen that the digital multiplexer is a combinational logic circuit which contains 1 to 4 control inputs, 2 to 16 data inputs, and 1 output. However, there are multiplexer circuits available which also provide a complemented output. The multiplexer may be considered an electronically controlled switch in which one of the data inputs is connected to the output. The input information being transferred to the output is determined by the control lines in the circuit. This method of selection is often referred to as data routing. Demultiplexing, on the other hand, is the reverse process, meaning data from a single source is routed to various destinations. The demultiplexers may be considered an electronically controlled switch whereby a single data input line may be connected to any one of several outputs. This concludes review number 2. Next, we will examine register circuits.